So hello everyone, I hope you can listen to me. So today we are going to see the next part called as multi-class classification. In last class we have proved that perceptron is trainable in finite number of steps. Star is provided problem is linearly separable. Okay, so in continuation to this, we will try to solve multi-class problem. What we saw in last class was a two-class problem. So same perceptron we will try to use for multi-class. Now this multi-category single layer network. So what it means, we have many categories. Say this O1 is class 1, this O2 is class 2, and so on up to class K. So these are all K different classes you want to learn, and each class is represented by one neuron. Okay, so this is neuron 1, then this is neuron 2, and this is neuron K. So there are K number of classes we want to learn. Then I should have K number of neurons. Okay, so straight away what you will do, you will take, suppose I want to learn 10 classes, then I will take 10 neurons, 10 perceptrons, and every perceptron will receive same input X and one more node fixed to plus or minus 1. So that doesn't make any difference. I can connect even to minus 1 as shown here, or even you can put it plus 1. So it's a thresholding thing. Automatically weights here will be adjusted. So if you put here minus and you want weight to be plus, then this will get automatically negative sign here. So Wn plus 1 becomes automatically minus 1 and vice versa. So this is not a significant issue. You can put here augmented say feature as plus 1 or minus 1. Combiningly, say this y is a vector with x, which is original feature vector, augmented by plus or minus 1. Okay, so this will be received by all the neurons. Okay, same input is coming to everybody, but what is changed is the weights. Weight of each neuron is different. And is responsible for that particular class. Say this is the weight here responsible for class 1, this is the weight here responsible for class 2, and so on. Okay, so how do I train all these things, and how I make the data representation for this particular problem. How do I represent desired response for this problem? So if you remember perceptron learning rule, so say W new is equal to W old plus delta W, which is equal to W old plus C into D minus O into say Y or X. Okay, so this is my regular perceptron learning rule for a single neuron. Now instead of single neuron, I have multiple neurons or many neurons. Then how do I do it? For each neuron, what we do is, for each neuron, we assign a class. Okay, say let us take one example of a 3 class problem, say 1, 2 and 3. So all of them are receiving same input vector x and one additional node for biasing, and let us say it is connected to -1. So this y is equal to x minus 1 is a input vector. So then node number 1 is responsible for class 1, node number 2 is responsible for class 2, node number 3 is responsible for class 3. Now when I present, suppose the pattern y1, I have to give a desired response for this input pattern. Now in this case it will be another vector. Okay, earlier it was a plus or minus kind of thing because we were having only one neuron. So for one neuron we may have +1 as in output desired response or -1. Now in this case, suppose y1 belongs to class say 1, then the corresponding desired vector. Now see carefully, I am saying corresponding desired vector, not desired response or number. It's a vector. Now what I do, I want, suppose y1 belongs to class 1, I want +1 here since this belongs to class 1, and for remaining I want -1. So +1 -1 -1. So this will be the desired response for the input which belongs to class 1. Now suppose I have some other input y2 which belongs to say class 2. Then what will be desired response? The desired response I will write as d2 bar equal to, now you see the change, I will require here -1 +1 at the second position and then again -1 at third position. Can you write on your own this third one? If y3 belongs to class 3, what will be desired response? So it will be a d3 vector, it will be -1 at third position. At third position I want +1. Okay, so this is the way we represent desired response. Okay, so now how do I represent my data? I just need some space here. Okay, so in general what we do is we take some matrix, the matrix say X, let us say some capital D data matrix. Then we arrange the vectors like this. Say this will be my input x1 or y1, then this can be y2, this can be y3 and so on up to how many? Suppose I have y capital N inputs. You can arrange like this. Then you can arrange corresponding, say, desired response matrix. Say, I can say DR, desired response. Then you can arrange like this. Say this will be D1, this can be D2, and so on up to Dn. So remember, this becomes now matrix because these individual responses, desired responses, are now vectors. So you can arrange like this or you can arrange in vertical form. So that doesn't make any problem, but you have to follow one convention. So you can arrange like this. So this will be D1, this will be D2, and so on. So you follow any one convention, say this or this. So depending on, you have to write the multiplication command properly. You have to match the dimension when you write a program. Now how I do training for such a network? So here we assume, first of all, randomly all weights for each neuron. Say I have k neurons, so each row here is dedicated for one neuron. So this is weight of neuron 1, this is weight of neuron 2, and so on. So this is weight of neuron k. Okay, so these are the weights, and this matrix W is called as weight matrix of the circuit. Suppose I have 3 neurons and a feature vector of size 2. So this one additional node becomes 3. Okay, so this is connected to everybody. Okay, so this is x1, x2, and connected to say -1. So this is neuron 1, 2, 3. Now see how I construct W. So this will be W11 weight. When I write W11, the first number, say W11, the first position is neuron number. So you keep this thing in mind. It will come in multi-layer also. The first position is neuron number, to which neuron this weight is associated, and the second number, second position, is from where it is coming, from where. So this is coming from position 1 of previous layer or from input side. So this weight is 1, 1. Now can you see what will be this? So this weight, suppose I want to write, then this is the third neuron, and say this is the connection connected to third position. So I can write W33. Instead of -1, I can write here x3. So that doesn't make any problem. So, but you have to see that in your program, x3 is always connected to -1. So W33 stands for third neuron, third input connection. Okay, like that, when I talk about neuron number 1, if I zoom this area and if I draw here, this will be W11, this is neuron number 1, then this will be W12, since this is coming from x2, and the third weight is W13, say it is coming from x3. So what we do, we write a W matrix with W11, W12, W13. Then if I want to write for second neuron, I will write W21. So I'm talking about now this position. So this is 21, 22, 23, then 31, 32, 33. Okay. So this is my W matrix for this circuit. Suppose you have 10 such neurons, then number of rows will increase, and if you have many features, the number of columns will increase. So when I say W matrix is of size K, capital K by say capital N, what it means, there are K number of classes in my circuit and say capital N number of dimensions. Generally we represent it by small, so I can write here small. Okay, so first step is to randomly assume weights for each neuron. So we don't know solution, straightway randomly assume a solution. Now next step is learning constant. So assume some learning constant, maybe say 0.1. Sometimes for simplicity we take 0.5. Okay, so you just choose as per your wish what will be learning constant. So it will control step size. Okay, so we keep a small number in the range of 0.1, 0.2 in practical. Now third step, you update the weights using perceptron learning rules. So I hope everybody now remembers this simple rule. Change in weight is added to old weight, it will give you new weight. Okay, and here C is the learning constant, D is the desired response, O is the output, and Y is input. Now fourth step is compute the error for each iteration, and if error is not 0, repeat above steps. In practical cases, since my data may not be linearly separable, I can say if error is less than or equal to some small number, then stop. Okay, practically we do like this. Now here weight updation is the main thing. How do I update the weight? Formula is given to you, but which neurons weight you are going to update? Now the key thing is you will update the weight of a neuron whose output is not equal to desired response. Say for example, this is neuron 1, this is neuron 2, this is neuron 3. My desired response, suppose D1 for input Y1 is say -1, +1, -1. This I expect for the input Y. But what I get is suppose +1, +1, and let us say again a +1. I obtain 3 +1s, and this is my output, and this is the desired response. So desired response is not matching with the actual output that is coming, or rather output is not matching with the desired response. Now which positions are not matching? So here I expect -1, but I got +1. Here I want +1 and I obtain +1. So this is the correct position. So here I got +1 and I expect -1. So there are two positions which are wrong, one position which is correct. So training has to be done on neuron 1 and neuron 3. Now how do you do? You use same formula, W new, W old plus delta W. Delta W is C into D minus O into Y. So this desired response for neuron number 1 is -1, output is +1. So you will update weight as per this formula for this individual neuron 1. Then you will use same formula with its desired response and output, corresponding output, and you will update weights there also. So here for first neuron you will use or update weights of first neuron, and then for third neuron you will change corresponding weights. Okay, this is how you will repeat these steps. Then you will take the pattern number 2, Y2, you apply to the updated network. Every time you have to take a new input and apply it to updated weight matrix. Do not use the initial weight matrix again and again. So what it means, you take Y1, you updated weight matrix W. So initially I will call this as W0. Once you update it, so it becomes W1. Then you will take Y2. You will check output using W1 as your weight, and then if required you will change the weight. So like that you will keep on applying the inputs. You have say n number of inputs and you can change your weights n times. So finally this will be your weight after one iteration. Hello class चल रहा है class. So this is the weight after presenting all training samples. So it completes your first iteration. So what is first iteration? It means you have presented all available training samples. Okay. Then if you are not satisfied with the error of this thing, error after one iteration, then you can re-enter into another cycle of training. So that becomes your second iteration. So you may have to do this many times. You means computer will do it, so don't worry about this. So you have some data set, say like this. So this is your data set. You will take y1, then y2 up to yn. You use all of them one by one, and at the end of this position you will calculate error. You are not satisfied with the total error, that means how many things you got wrong, then you can go back. You again enter into another cycle. Now there is a small thing that you should remember. What we saw was the binary neuron, that is plus or minus kind of thing. Now instead of that, suppose I use continuous activation function like tanh function or logistic function, then we call this network as single layer continuous perceptron training. Okay, so single layer stands for many classes, continuous stands for the activation function used. The other things are same, that means you have to randomly assume weights, learning constant, then update weight using now continuous perceptron. Now what will be changed when you go to the perceptron with continuous activation function? This delta W will change. So this delta W is equal to this quantity C into Di minus Oi. So this extra term will come because of this continuous activation function into Y. So this is nothing but your delta learning rule. So we have to use delta learning rule when we go for continuous activation function. We will use perceptron, original perceptron learning rule when we go for the binary neurons, like plus or minus, outputs are plus or minus 1. Okay, so only thing is we have to compute O dash, we have to compute O dash to calculate delta W. I will take one example so that these things are more clear. Now important thing you should note is when I go for tan H activation function, that means output is equal to tan hyperbolic of net value. So we can write this output of ith neuron as OI equal to twice divided by 1 plus e to the power minus net minus 1. So what it is doing, it is just multiplying your multiplying your logistic function by 2 and subtracting minus 1 from it. So that we have seen when we saw activation functions. So our logistic function is like this. It is in the range 0 to 1, some S-shaped function. So you can see like this. And if I multiply this function by 2 and subtract minus from this, so it will be a function of this shape which ranges plus 1 to minus 1. So if I differentiate this term with respect to net, I will get this quantity. Sorry, not this one. If I multiply this and solve, I will get this quantity. And if I differentiate this with respect to net, then I will get this particular thing, half into 1 minus OI square. So what it means is, to compute O dash, I just need to compute output of the neuron. So let us say this is a neuron which produces output OI, says this is some ith neuron. These are some inputs. So I calculate net here. This net I will substitute into this equation, say this equation, which will give me some output OI. Then I need f dash of this or OI dash of this. How do I obtain? So OI dash is equal to OI dash is equal to half into 1 minus OI square. So you just square this output and subtract from 1, divide by half, say divide by 2. So that will give you f dash or oi dash, and use that in your perceptron learning rule so that you will get change in weight. So I know that this is W old plus C into DI minus OI into OI dash into Y. So this OI dash I can replace with some C into DI minus OI into half into 1 minus OI square into Y. So this half I can absorb in this constant C, so I can write this as W old plus some C di minus OI into 1 minus OI square into 1. So this is my change in weight rule when I use sigmoidal, say bipolar sigmoidal activation function. Okay, so there will be a small change if I go for logistic function. So logistic function, that means it will range from 0 to 1. It's a S shape, and it is given by 1 upon 1 plus e to the power minus net. So f dash of that, or derivative of that with respect to net, is OI into 1 minus OI. So this quantity is OI dash. So OI dash, if you substitute in your perceptron continuous learning rule, so it will be the modification of that rule. So W new is equal to W old plus C into DI minus OI into 1 minus OI square into 1. So you will use, say, equation number 2 when you are using, say, tan h function. You will use equation number 1 when you are using logistic function. Remember, logistic will range, will give you output in the range 0 to 1, and your tan h will give you output in the range minus 1 to plus 1. So we will take one example, and we will take first of all with a discrete perceptron. Let us say we have 3 samples which belong to 3 different classes. So this is a class 1 sample, this is a class 2 sample, and this is a class 3 sample. Okay, and these are the corresponding desired responses. So since this is a class 1 sample, you will see at this first position I have plus 1. Say for second sample I have plus 1 here, and for third sample I have plus 1. So for simplicity, I am just taking 3 samples, and they do belong to 3 different categories. In practical cases, you will have many samples belonging to, say, 3 or more classes. Now randomly, first of all, say assume the weights for each neuron. How many neurons? Since you want to learn 3 classes, you will take 3 neurons. Okay, so 3 neurons because I have 3 classes to be learned. For each neuron, how many inputs? So for each neuron, since my input is 2 dimension, 1 dimension is extra added for biasing, so it becomes 3 dimension. So this will be actual circuit. Okay, so this will be x1, this will be x2, and let us say this may be connected to plus or minus 1. So if I say this is the randomly assumed weight for neuron number 1, okay, for the first step, then it will be 1 here, minus 2 here, and 0 here. Okay, then for second neuron, it is 0 here, then minus 1 here, 2 here. For the third one, it is 1 here, 3 here, and minus 1 here. Okay, so this is a cleaner version of that. So I have initial weight here for neuron 1. Okay, we can call it as W11. Then this is W21 and so on. This is W31. Now, first step is to calculate the output for the network. So what we have to do, we have to use sine function because I am implementing discrete perceptron, so it will use sine function. So sine function you take for first neuron, so this is neuron 1 output, this is neuron 2 output, and this is neuron 3. You take weight, corresponding weight, and multiply your first input, that is y1. So y1 will go with everybody, and you will calculate output here, and you can check this. It's what will be net value. So net value for first neuron is 1 into 10, 10 minus 4 plus 0, so it will be 6, and sign of 6 is positive, so this is positive. Similarly, 10 into 0 is 0, so minus 2, and this will be again minus, so this will be minus 4, and sign of that is negative, so this will be minus 1. Similarly, 10 plus 6 plus 1, so sign of this is positive, so I will get plus 1. But what is desired response for input number 1? So desired response for input number 1 is plus 1 minus 1 minus 1. What you obtain? You obtain here plus 1. This should be minus 1. This should be minus 1. But you got two things right. This is right. This is right. But third one is wrong. So you want for third position minus 1, but you got it plus 1. So what you will do? You will train your neuron number 3 for input number 1. So whichever neuron is producing wrong answer, you will treat that neuron properly. Let us say learning constant is 0.5. You will calculate, depending on that, what is you will calculate change in weight for neuron number 3 only. Okay, and you will use this third weight, updated weight, for next input. You can see here for second input, for neuron number 1, weight is not changed. For second input or second step, weight for neuron 1 and 2 is not changed because they are producing correct answers. Okay, now we are updating only for neuron 3 because it is producing wrong answer. Now updated weight using perceptron learning rule is this one, minus 9, 1, 0. Now you take second input, that is 2, 5, minus 5, minus 1. You multiply with weight of each neuron again. So this is weight of neuron 1, this is weight of neuron 2, this is weight of neuron 3. Remember, this is updated weight. This is updated weight. Now when you multiply, you will get plus 1 here, plus 1 here, minus 1. What is desired response? Desired response for second input was minus 1, plus 1, minus 1. So who is producing wrong answer? So this position is wrong. These two are correct. So we will not disturb neuron number 2 and neuron number 3. We will update only weight for neuron number 1. I can see here I am updating weight for neuron number 1. It has changed from 1 to 0 to minus 1, 3, 1. So this is new value. Remaining two neurons are producing correct answer. So this is kept as it is. Now we can go for third input, that is Y3, and you can try at home. This is the Y3 out. This is the neuron number 1 output for step 3. This is neuron 2. This is neuron 3. What is desired response? Desired response is minus 1 here, minus 1 here, plus 1 here. So where is wrong answer? So this is correct. This is also correct. So this position is wrong. So neuron number 1 is again producing wrong answer. So you will treat neuron number 1. You will get some updated weight like this, and the remaining two neurons are as it is. So if you do like this, keep on doing like this, after 9 iterations, say you will get a correct settlement of your neurons, and you will get this weight or implementation of this particular decisions lines after say 9 iterations or so. So what it means and how different classification regions are appearing, that we will see in next class. So I can show you that right now. So these are the classification regions, and so I'm saying that these three lines are now implemented by 3 neurons. So this is line number 1 by neuron 1, this is line number 2 by neuron 2, and this is line number 3 by neuron 3. So this is the region. This is the region for class 3. This is the region for class 1, and this is the region for class 2. Okay. So this is how you can say multi-class problem is solved using same two-class neurons. So using many two-class problem, or combining say 1 versus rest. That means for each neuron, suppose for neuron 1, training data which belongs to class 1 is should produce plus 1, and the rest, that is for class 2, class 3 up to class k, it will produce minus 1. So when you take neuron number 2, it will produce plus 1 for class 2, and for other classes, that is 1, 3, 4 up to k, it will produce minus 1. So it is basically the approach is 1 versus rest. In that fashion, we are going to train this system. So as a homework, you can solve above problem using continuous activation function. Okay. So you refer to your book this problem is available there, and if you have any doubt, we can talk in next class. So let us stop here.